In the heart of the cosmos, a star once blazed with unimaginable brilliance. Its light streamed across the gulfs of space, weaving shadows on worlds that would never know its name. For millions of years, it burned as a furnace of creation, forging heavy elements in the crucible of its core: carbon, oxygen, iron, the seeds of planets, oceans, and life itself. It seemed eternal, a beacon of permanence in an impermanent universe, but every star is born with an ending written into its beginning. For this one, the end came not as a gentle fading, but as a catastrophic silence. Gravity, once held at bay by the fire of fusion, reclaimed its dominance. The star's brilliance faltered, its core collapsing in upon itself with irresistible force. Light bent inward, crushed by gravity's demand. The nuclear fire was extinguished. What remained was neither flame nor ash, but an absence so complete it defied comprehension. A colossal star, more massive than 1,000 suns, had vanished. No light escaped, no message of its death crossed the void. It had not exploded into glory. It had simply disappeared. A star that once illuminated galaxies now sank into nothing, leaving only the silence of the void behind. Where did it go? Did it truly vanish, erased from existence, or does it linger in a form unseen? What remains when the heart of a star collapses? Beyond the reach of matter, beyond the reach of light, beyond even the reach of time. This is the birth of a black hole. A star that has sunk into nothing, and in doing so has opened the deepest mystery of the universe itself. Long before equations and telescopes, long before physics had a language, humanity lifted its gaze to the night sky and found eternity written in fire. To the ancients, stars were not transient things. They were immortal torches set against the firmament, their slow procession across the heavens, too steady to suggest birth or death. Egyptian priests charted their rising and falling. Mayan astronomers carved their motions into stone. Greek philosophers debated their essence. Yet in every age, stars were seen as eternal. Eternal fires in the heavens, unchanging, incorruptible. If earth was fleeting, the stars were permanence. But within the heart of each star lies a secret truth. Every point of light that burns in the night sky carries within it a clock, ticking toward collapse. This realization would not arrive for millennia. For thousands of years, humanity believed in cosmic stillness. Only in whispers, only in imagination, did the idea of a vanishing star first appear. In the late 18th century, to thinkers, John Michell in England and Pierre-Simon Laplace in France, planted the first seeds of what would later be called the black hole. Working from Newton's laws of gravitation and the finite speed of light, Michell asked a question that sounded like philosophy rather than physics. What if a star's gravity was so immense that even light could not escape? He called it a dark star. Laplace reached a similar conclusion. They imagined colossal suns collapsed into invisibility, their presence betrayed only by their pull upon nearby objects. Their vision was ahead of its time. For 2 centuries, the idea lay dormant, a curiosity more than a prediction. No one had yet glimpsed the physics that could make such monsters real. Then, in the early 20th century, the fabric of science itself shifted. Albert Einstein unveiled his theory of general relativity in 1915, and with it, a new understanding of gravity. Gravity was no longer a force acting at a distance, as Newton described, but the curvature of spacetime itself. Massive objects bend. The fabric of reality and light, following the curves of this geometry, bends with it. Suddenly, the speculation of Mitchell and Laplace gained new meaning. If space could curve, then perhaps it could collapse. If light could bend, then perhaps it could be trapped. Einstein himself doubted the extreme implications. The equations of relativity, solved under the simplest conditions by Carl Schwarzschild in 1916, produced a strange and troubling result, a radius beyond which nothing, not even light, could escape. It was the mathematics of a black hole, and yet Einstein resisted. He believed nature abhorred infinities that singularities could not form. For him, the equations had yielded a mathematical oddity, not a physical reality, but the universe has little regard for human doubt. In the 1930s, a young Indian physicist named Subramanian Chandrasekhar, sailing from Bombay to England, carried in his mind the mathematics of collapsing stars. He calculated that if a star's mass exceeded a certain limit, about 1.4 times the mass of the Sun, no force could hold it up once fusion ceased. Electron degeneracy pressure, the quantum resistance that supports white dwarfs, would fail. Beyond this threshold, gravity would crush the star with unstoppable force. His numbers were correct. His conclusions, however, were met with hostility. At a famous debate in London in 1935, Sir Arthur Eddington, one of the most revered astrophysicists of the age, dismissed Chandrasekhar's idea as absurd. Nature, he argued, would not allow such a catastrophic collapse. Stars could not simply disappear. The meeting humiliated Chandrasekhar. For decades, his insight lingered in the shadows, a truth unrecognized. Yet truth has a way of resurfacing. That same decade, in 1939, two American physicists, J. Robert Oppenheimer and Hartland Snyder, extended Einstein's equations to model the fate of massive stars. Their results were chilling. They described an object collapsing so completely that, to an outside observer, time itself seemed to freeze at its boundary. They called it a frozen star. It was the first theoretical description of what we now know as a black hole. But Oppenheimer's work arrived at the brink of war. Attention turned to weapons, not stars, and his insight was largely forgotten. For nearly 2 decades, skepticism prevailed. The concept of a star collapsing into nothingness seemed too extreme, too violent, too final. Many physicists believed that unknown laws of nature would intervene, halting collapse before the abyss could form. Black holes were relegated to speculation. Mathematical curiosities whispered about, but not embraced. Then, in the mid-20th century, the universe itself began to reveal its secrets in new ways. Radio astronomy opened invisible windows on the sky. Astronomers detected quasars, quasi-stellar radio sources, brighter than entire galaxies, yet compact enough to fit within a solar system. Their power could not be explained by ordinary stars. By the 1960s, it became clear. Quasars were fueled by matter falling into supermassive black holes at the centers of galaxies. The cosmos was not hiding these monsters. It was blazing with their energy. Closer to home, binary star systems betrayed another clue. In systems like Cygnus X1, an unseen companion tugged at its partner star, drawing matter into an accretion disk. As this material spiraled inward, it released torrents of X-rays, a beacon of destruction. The visible star circled not another star, but something invisible, dense, and consuming. For the first time, astronomers had found a stellar mass black hole. The shift was irreversible. What had once been dismissed as impossible became undeniable. The star that sank into nothing was not a myth, not a mathematical trick. but a reality, written into the structure of space by the 1970s. The language of black holes entered both science and culture. Stephen Hawking, Roger Penrose, and others showed that the formation of singularities was not only possible but inevitable, given the right conditions. Hawking, in particular, would transform the black hole from an astrophysical oddity into an crucible for the deepest questions of physics. From ancient skies, where stars seemed eternal, to telescopes that revealed their vanishing, the story of black holes is the story of a profound shift in human thought. Stars, once symbols of permanence, could die not in fire, but in silence, sinking into nothingness, leaving behind only their gravitational echo. The discovery was not simply scientific, it was existential. If stars, those ancient guardians of the night sky, could collapse into invisibility, then permanence itself was an illusion. The cosmos was stranger, darker, and more fragile than anyone had imagined. And yet, within this fragility lies a new kind of wonder. The star that sank into nothing did not vanish entirely. It left behind a riddle, a doorway, a question that even now stretches the limits of physics and philosophy alike. What, truly, lies beyond the horizon of a black hole? The discovery was only the beginning. The shock was yet to come. The realization struck science like a thunderclap. Stars, those ancient forges of light, could collapse into invisibility. What had been dismissed for centuries as a theoretical curiosity now loomed as a real, physical phenomenon. The shock was not merely astronomical, it was philosophical, existential, a rupture in the very fabric of human understanding. At the center of this rupture lay a word that seemed harmless in everyday life: singularity. In mathematics, a singularity is simply a point where equations break down. But in physics, applied to the collapse of a star, it became something far more terrifying. At the heart of a black hole, all the matter of a massive star, millions of times the mass of Earth, is crushed into an infinitely small point. Density becomes infinite, space-time curvature becomes infinite, and the laws of physics, as we know them, disintegrate. Einstein's general relativity, so successful in describing the motion of planets, the bending of starlight, and the geometry of the cosmos, falters at the singularity. It does not tell us what lies beyond. Physics itself seems to dissolve in the core of a black hole. For the first time, science confronted a place where its own language failed. But the singularity was not the only shock. Surrounding it lay an invisible boundary, a threshold that would redefine reality, the event horizon. This was the point of no return, the invisible sphere beyond which escape was impossible. Not even light, racing at the ultimate speed limit of the cosmos, could flee once it crossed this horizon. For any star collapsing beyond its critical radius, this was the fate, to vanish behind a veil that concealed it forever. The concept was staggering. The universe, thought to be a stage where all could be observed and measured, contained hidden places, sealed off from view. The event horizon was not a physical surface, no matter, no fire, no shell. It was geometry itself, space-time folding into an unseen barrier. To cross it was to fall into silence, forever severed from the outside world. But with this realization came a paradox. If a star's material fell into a black hole, then all information about its structure, its history, its composition, everything that made it what it was, seemed to vanish beyond the horizon. To a physicist, this was heresy. The principle of conservation of information, sacred to quantum mechanics, was violated. If information could be erased from the universe, then the laws of physics themselves were not laws at all, but suggestions. This conflict set the stage for one of the greatest scientific crises of the 20th century, the information paradox. On one side stood Einstein's relativity, declaring that black holes swallow everything and hide it forever. On the other stood quantum mechanics, insisting that information cannot be destroyed, only transformed. The two pillars of modern science collided at the horizon of a black hole, and the tremors have not yet ceased. The emotional weight of this shock was immense. Stars, for millennia, had been symbols of permanence, of eternity. They guided travelers. Across deserts and seas, they served as metaphors for immortality in poetry and myth. Yet physics revealed that they were not eternal at all. They could collapse into graves invisible to the cosmos. The star, the very emblem of constancy, could sink into nothingness. And with this collapse came a terrifying implication. If stars could fall, what about everything else? Was the universe itself susceptible to a similar fate? Could space-time itself collapse, not into stars, but into nothingness? The shock deepened with further exploration of black hole geometry. As relativity was applied more carefully, new models emerged. Rotating black holes, described by Roy Kerr in 1963, added layers of complexity. A spinning black hole was not simply a sphere, but a dynamic storm of space-time, surrounded by an ergosphere, a region where space itself is dragged around at near light speed. Within this realm, nothing can stand still. Energy can even be extracted, as if the black hole were a cosmic engine. Such predictions were almost unthinkable. A star's death could yield not only silence but motion, power, a twisting of reality itself. Here was not only annihilation but transformation. Yet it all stemmed from the collapse into a singularity, a place where the known laws of physics evaporated. Adding to the astonishment was time itself. Near a black hole, time dilates, slowing under the crushing pull of gravity. To an outside observer, an object falling toward the event horizon never quite crosses it. Its light grows redder, fainter, stretched by gravity until it vanishes in silence to the falling object. However, the crossing occurs in finite time. Two perspectives, two realities, both true and irreconcilable. Time, thought to be absolute, fractured at the horizon. For scientists and philosophers alike, this was unsettling. Black holes did not merely challenge ideas about stars. They challenged the very structure of existence: matter, energy, space, time, and information. Each was twisted, erased, or thrown into paradox. Then, in the 1970s, Stephen Hawking added an even greater shock. Building on quantum field theory, Hawking showed that black holes are not entirely black. At their horizons, quantum fluctuations give rise to particles and antiparticles. Occasionally, one particle falls in while the other escapes, appearing as faint radiation. Over immense timescales, this Hawking radiation allows black holes to lose mass, to evaporate, to disappear. This revelation was staggering. Black holes, once thought eternal prisons, could themselves die. But if they vanish, what happens to the information they contained? If the radiation carries it away, then perhaps information is preserved, but Hawking's original calculations suggested otherwise. The radiation is thermal, featureless, containing no imprint of what fell in. Information still appeared to be lost. Thus the paradox sharpened. If black holes evaporate, do they erase reality itself? Or does information survive in some hidden form on the horizon, in quantum entanglement, or in structures science has yet to uncover? The scientific shock of black holes lay not only in their existence, but in their implications. They revealed limits of observation, breakdowns of laws, paradoxes of information, distortions of time. They forced physics to confront the possibility that its own foundations might be incomplete. For humanity, this shock rippled beyond science. It challenged the meaning of permanence. It transformed stars, once eternal symbols, into fragile beings destined for silence. It raised questions about the nature of reality itself. Is existence stable? Or does it hide fractures waiting to consume it? The star that sank into nothing had done more than collapse. It had pulled thought itself into its orbit, dragging science into an abyss of paradox and mystery. The discovery was astonishing, but the true work of science had only begun. To face this abyss, deeper investigation was inevitable. The shock of black holes had shaken physics to its foundations, yet science does not retreat from the abyss. It stares deeper into it. The collapse of a star into nothingness was no longer only a theoretical puzzle. It became a challenge for observation, experiment, and mathematics. If stars could sink into invisible graves, then their presence must leave traces, shadows, signals. The universe, though silent, was not mute. The first clues came from the study of binary star systems. Astronomers noticed certain stars orbiting invisible companions. One partner shone brightly, radiating in X-rays, while its counterpart remained unseen, pulling fiercely upon it. Matter from the visible star streamed toward the dark companion, spiraling inward at near light speed. In this dance, the infalling matter heated to tens of millions of degrees, glowing in X-rays before vanishing. What could be massive enough to pull with such strength, yet remain invisible? The answer was inevitable: a black hole. In the 1960s and 70s, discoveries of these X-ray binaries, such as Cygnus X1, gave the first compelling evidence. Here was a star's corpse, not a neutron star, not a white dwarf, but something darker. A star had indeed sunk into nothing, leaving only its gravitational hunger behind. Theories were no longer abstract. Black holes were real. Beyond binaries, the universe unveiled even more dramatic clues. Quasars, discovered in the 1960s, shone brighter than entire galaxies, yet their light originated from regions smaller than our solar system. What furnace could power such brilliance? Only one answer fit: supermassive black holes, millions or billions of times the sun's mass, feeding on the matter around them. As material spiraled inward, it released gravitational energy with efficiency unmatched by nuclear fusion. These beacons, billions of light years away, announced that black holes were not rare monsters. They were central engines of cosmic evolution. The physics of these accretion disks became a new field of study. Spirals of gas, dust, and even stars, heated and torn apart, radiated across the spectrum. Relativistic jets erupted from their poles. Streams of plasma accelerated to nearly the speed of light. Here was a paradoxical truth. The darkest objects in the universe produced some of its brightest phenomena. The star that sank into nothing still spoke, not in light of its own, but in the fiery scream of what it consumed. The deeper investigation also turned to the geometry of spacetime itself. Black holes were not just astrophysical objects. They were laboratories for fundamental physics. Around them, space curved and time stretched. Light bent into rings, creating gravitational lenses. To peer near a black hole was to see relativity at its most extreme. Mathematical models expanded. The Schwarzschild solution described non-rotating black holes, while Roy Kerr's solution unveiled the strange beauty of rotating ones. In a Kerr black hole, space itself is dragged around, twisting everything caught within. The ergosphere allowed for energy extraction, a process known as the Penrose mechanism. The implications were astonishing. A collapsed star could become not only a sink but a source, a cosmic dynamo of unimaginable power. Yet perhaps the greatest turn came in the 1970s, when Stephen Hawking and Jacob Bekenstein reframed black holes, not as silent voids, but as thermodynamic systems. Bekenstein proposed that the surface area of the event horizon corresponded to entropy, a measure of information, disorder, or hidden microstates. Hawking, extending this reasoning, showed that black holes must radiate. From the froth of quantum fields at the horizon, particles emerged, carrying away energy. A black hole, long thought eternal, could evaporate. This revelation deepened the paradox. If black holes evaporate, what becomes of the information about the star that created them? If radiation carries no imprint of the past, then the universe suffers amnesia. Information is gone, destroyed, something quantum mechanics declares impossible. Here, in the silent corpse of a star, lay a puzzle that could fracture the foundations of science. The search for resolution led to quantum gravity, an attempt to unite relativity and quantum mechanics. In this quest, black holes became the crucible. Simulations of stellar collapse suggested that singularities were inevitable, yet theoretical frameworks like loop quantum gravity and string theory hinted they might be avoided. Perhaps singularities are smoothed by discrete spacetime or hidden dimensions. Perhaps collapse leads not to nothingness, but to transformation. Meanwhile, observational astronomy reached further. Telescopes mapped gravitational lensing arcs of light bent by unseen masses, betraying the presence of black holes. Satellites such as Chandra and XMM Newton recorded excises from accretion disks, measuring their temperatures and dynamics. Each observation refined the picture. Black holes were not merely graves. They were dynamic participants in the life of galaxies, shaping their growth, sculpting their stars. Then came the dawn of gravitational wave astronomy. In 2015, LIGO detected ripples in spacetime from the merger of two black holes. Here was direct evidence, not of theory, not of distant speculation, but of black holes colliding in violent cosmic dances. Stars that had once burned now moved spacetime itself, sending echoes across billions of light years. The star that sank into nothing had not vanished entirely. It had become a ripple in the fabric of existence. Simultaneously, simulations of stellar collapse grew in sophistication. Supercomputers modeled the implosion of massive stars, the rebound of shock waves, the formation of horizons. They showed the moment when nuclear fire flickered out, when gravity overwhelmed all resistance. The collapse into a black hole was not a clean transition, but a chaotic storm. A last burst of light before silence. Black holes also revealed strange optical illusions. Near the horizon, light orbited in unstable paths, creating shadows and rings. In 2019, the Event Horizon Telescope delivered humanity's first direct glimpse, the shadow of M87*, a supermassive black hole. For the first time, a star's collapse into nothing had been photographed, not in detail, but in outline, a dark circle rimmed by fire. Each investigation, each observation added depth to the mystery. Black holes were real, measurable, yet still paradoxical. They obeyed physics, yet they mocked its laws. They consumed information, yet they hinted at holographic secrets. They were silent, yet they roared through quasars, jets, and gravitational waves. The deeper science probed, the more profound the questions became. Were singularities truly points of infinite density, or signs of incomplete theories? Did Hawking radiation erase information, or was it somehow encoded in subtle correlations? Was the horizon a surface, a firewall, or a hologram? The deeper investigation made one truth clear: the collapse of a star was not the end of inquiry, but its beginning. Black holes were no longer astrophysical curiosities. They had become crucibles of physics, intersections where relativity, quantum mechanics, thermodynamics, and information theory collided. For humanity, this was humbling. The universe had revealed one of its most dramatic transformations, a star sinking into nothing, only to leave behind riddles that pierced to the heart of reality. To study black holes was not only to understand stellar death, but to approach the ultimate nature of space, time, and knowledge itself. The star that collapsed had not vanished quietly. It had become the most eloquent paradox the cosmos had ever written, and as science peered deeper, the mystery only grew darker. The deeper science pressed into the nature of black holes, the more the mystery refused to yield. Instead of resolving, it escalated. What had begun as a single star collapsing into nothingness became a cosmic riddle that stretched across galaxies, across time, and perhaps beyond the universe itself. The star did not simply die. Its silence echoed louder with every discovery. Black holes, once thought rare and exceptional, revealed themselves to be central architects of the cosmos. At the heart of nearly every galaxy, including our own, a supermassive black hole resides. In some galaxies, they weigh millions of solar masses, in others, billions. Their gravity organizes the orbits of stars, influences galactic evolution, and drives the jets that pierce intergalactic space. The collapse of one star seemed insignificant against these titanic behemoths. Yet they shared the same origin, a surrender to gravity so absolute that nothing, not even light, could escape. But with their ubiquity came unease. If galaxies needed black holes to form, then the universe was shaped by the very objects that appeared to erase existence. The paradox grew sharper. Creation and annihilation bound together. The death of stars was not an end but a condition for cosmic life. Then came the most haunting realization of all. The horizon itself was not stable. It was a boundary in retreat. With every moment, as black holes merged, as they accreted matter, their horizons grew. In this growth lay erasure. Galaxies falling into black holes would not simply be consumed. Their histories would vanish from the observable universe. Concealed beyond the horizon, the Event Horizon Telescope's image of M87* intensified this feeling. The black circle was more than a shadow. It was a scar on reality, a place where laws of physics broke, where the language of science fell silent. Humanity, for the first time, gazed directly at the edge of knowability, the last surface a star ever paints. Upon existence before sinking into invisibility, the mystery deepened as the paradox of information reached a crisis. If a star collapses, its chemical composition, its structure, its history, all the information it contains seems to vanish behind the horizon. Yet quantum theory insists information cannot be destroyed. Here, the two greatest pillars of physics stood in direct conflict. General relativity described the smooth, unstoppable collapse of the star. Quantum mechanics demanded conservation, memory, order. The black hole stood between them, mocking both. From this clash emerged the holographic principle, the idea that the three-dimensional universe we see may in fact be encoded on two-dimensional surfaces, just as information about a star might be stored on the horizon of its collapse. If true, then the star had not vanished. Its essence lingered, etched into the geometry of spacetime itself. But if false, the universe itself might suffer from a kind of forgetfulness, a cosmic dementia in which history erodes irretrievably. The mystery grew darker still with the suggestion of firewalls. If the horizon were not smooth, but violent, then any particle, any astronaut, any star crossing it would be obliterated instantly. The star that sank into nothing would not pass quietly through a surface, but disintegrate in a searing wall of quantum energy. This contradicted Einstein's principle of equivalence, the idea that freefall is smooth. To accept firewalls would be to accept that relativity breaks down at the most fundamental level, and then, as if the paradox were not severe enough, black holes revealed themselves as bridges. Mathematical solutions suggested wormholes, tunnels through space-time that could in principle connect distant regions or even spawn new universes. Could the star that collapsed have seeded a cosmos of its own? Could what we call nothing be the womb of everything? Speculation grew into awe. Perhaps our own universe was born in the collapse of a star from another. Perhaps every black hole is a portal to elsewhere, the silence of a grave masking the birth cry of a new reality. The star had not sunk into nothing, but into an infinity of possibilities, yet none of these answers erased the dread. Because while theories stretched toward elegance, the observable universe whispered another truth. Horizons are dying pulses. As the cosmos expands, galaxies recede beyond reach. There, light, red-shifted and weakened, fades. One by one, they slip beyond the cosmic event horizon, never to be seen again. In the far future, only the faint glow of local stars will remain until they too burn out. Beyond that, only black holes, evaporating over unimaginable timescales, radiating away into silence. In such a vision, the collapse of a single star becomes a metaphor for the entire cosmos. All stars, all galaxies, even all black holes, will eventually vanish into hawking radiation, into whispers of heat, into nothing. The universe itself may sink into the silence, once reserved for a single star. This escalation of mystery carried with it profound philosophical weight. What does it mean for existence if memory itself can vanish? If the story of a star, the information of its atoms, the record of its being can be lost, then reality is not eternal but fragile. Knowledge itself becomes temporary. The cosmos may be vast, but it does not promise permanence. The deeper fear was existential. If stars can vanish into nothing, so can all that is made from them: planets, life, consciousness. Humanity's story, too, could be written on fragile waves of probability, destined to collapse into silence. The black hole does not only erase stars, it mirrors the fragility of existence itself. Yet amid this dread was wonder. Black holes, the ultimate symbols of annihilation, were also revealed as the sculptors of cosmic structure. Without them, galaxies would not form, stars would not be gathered, planets would not orbit. Without them, there might be no place for life to emerge at all. The star that sank into nothing may have given rise to the very conditions for beings to ask where it had gone. The mystery deepened not only in the language of equations, but in the silence it imposed upon human thought. Each discovery opened further horizons of paradox. Each explanation raised darker questions. In black holes, science encountered not merely objects of collapse, but mirrors that reflected its own limitations. The star that vanished revealed the fragility of knowledge, the incompleteness of theory, and the boundless strangeness of the cosmos. In the growing darkness of this mystery, one truth burned brighter. The deeper the star sank into nothingness, the more it illuminated the infinite questions still to come. When the star sank into nothing, the silence it left behind was not the end of inquiry, it was the beginning of speculation. Science, standing before the black horizon, has been forced into its most daring conjectures. Each theory is not only an attempt to explain what lies beyond the collapse, but also a reflection of how fragile human understanding becomes when pressed to its limits. The first of these conjectures came with Hawking's great revelation. Black holes are not perfectly black. They radiate. From the vacuum itself, particles emerge, borrowing energy from the black hole's mass. Slowly, across eons longer than the lifespans of stars or galaxies, a black hole evaporates. What seems like eternal silence is instead a whispering loss, a slow unraveling. But Hawking's insight sharpened the paradox. If radiation carries no imprint of what fell in, then information is gone forever, a violation of the deepest principles of quantum mechanics. If it does carry memory, then the horizon somehow encodes every detail of the star that sank. Which is true? The answer remains elusive. From here, speculation deepened into firewalls, invisible boundaries that may sear anything crossing the horizon into pure energy. In such a model, the star does not pass gently into shadow. It is violently erased at the boundary itself. But this contradicts Einstein's prediction that nothing special should be felt at the horizon. If firewalls exist, relativity bends. If they do not, then quantum mechanics falters. Either way, the star's collapse forces physics toward fracture. The holographic principle emerged as a possible escape. Proposed by Gerard T. Hooft and expanded by Leonard Susskind, it suggests that the universe may be like a vast hologram. Just as a two-dimensional film encodes a three-dimensional image, so too might the horizon encode the star that disappeared. If so, then information is never lost. It is inscribed in the geometry of spacetime itself, etched like ancient writing upon the fabric of the horizon. In this vision, the star has not vanished into nothingness. It has been translated, preserved in a hidden script that the universe itself is still learning to read. Yet other speculations went further. Some physicists suggested that the collapse of stars may not end within our universe at all. Instead, the singularity could serve as the seed of a new cosmos. Within the crushing gravity beyond the horizon, space-time could pinch and bud off, inflating into a universe of its own. In this model, the death of one star is the birth of another universe. Perhaps our own Big Bang was nothing more than the silent collapse of a star from another reality, unseen but connected. The star that sank into nothing may, in truth, have become a genesis elsewhere. Loop, quantum gravity offers yet another path. In this framework, space-time itself is quantized, built from finite loops rather than smooth continua. In such a universe, singularities cannot truly form, for infinities are forbidden. Instead, the collapse halts at a smallest possible scale. The star does not fall into infinite density, but into a new state. Perhaps a bounce, perhaps a bridge, perhaps a restructuring of reality. The horizon hides not a tear in physics, but a door into discrete geometry. String theory, weaving reality out of vibrating filaments in higher dimensions, proposes its own visions. Black holes may not be points of collapse, but tangled brains, where extra dimensions fold and knot. In such models, the star has not vanished into nothing. It has dissolved into deeper architecture, into strings vibrating in spaces beyond perception. What seems like silence may be a resonance we cannot yet hear. Then came the audacious conjecture of equals epor, suggested by one Maldacena and Leonard Susskind, that entanglement and wormholes are the same. If true, every pair of entangled particles is connected by a thin bridge of space-time. On the largest scale, a black hole's interior may not be isolated annihilation, but a portal. The star's collapse, then, may thread connections to distant regions of the universe, or even to realms outside it. To sink into nothing may be, paradoxically, to link to everything. Other ideas reach into cosmological futures. In a universe dominated by dark energy, black holes may evaporate into a vast, empty de sitter space, their last quantum whispers encoded on a cosmic horizon that itself behaves like a black hole surface. The star that once burned with light becomes part of a final heat death, its information smeared across an expanding boundary that swallows even memory. More speculative still is the suggestion that black holes are simulations of a deeper order. Just as computer codes compress data, horizons may compress the complexity of reality into surfaces, creating illusions of depth. The star's collapse into nothing may be akin to data compressed into a cosmic archive, retrievable only with equations we have not yet conceived. Every speculation circles the same abyss. Did the star truly vanish, or was it transformed? Does the horizon erase or preserve? Is the singularity destruction or creation? Each theory gestures toward different answers, but none close the riddle. What lies beyond remains veiled, and yet, in this uncertainty, a new kind of awe emerges. For black holes do not merely challenge physics, they demand philosophy. If the universe is holographic, then reality itself is projection. If stars spawn new universes, then existence is an infinite chain of births, each hidden in the death of another. If entanglement is geometry, then connection is woven into the fabric of being, across horizons and time. In this speculative theatre, the star that sank into nothing becomes more than a celestial corpse. It becomes a symbol of transition between theories, between realities, between what is known and what is forever hidden. The silence it leaves behind is not absence, but invitation to imagine, to calculate, to seek. The greatest speculation of all may be the simplest, that nothing is not truly nothing, that the void itself holds structure, rules, potential, that what appears erased is only transformed beyond recognition. The star has not disappeared. It has passed into a chapter of the cosmos that we have not yet learned to read, and so the question deepens, theories proliferate. None yet reign supreme. All attempt to answer the silence left by a star's collapse. But perhaps the truth is stranger still. Perhaps the star did not sink into nothing. Perhaps it sank into everything. The star that sank into nothing did not leave humanity powerless before its silence. It left a trail of questions, faint as cosmic whispers, that could be pursued with instruments of precision and patience. In the modern age, astronomy and physics are not bound to naked eyes or crude lenses. They are armed with observatories that listen to spacetime itself, satellites that scan the cosmos across invisible wavelengths, and laboratories that recreate echoes of collapse within fragile quantum systems. The star is gone, but the tools it inspired have grown into cathedrals of inquiry. The first of these great ears of the cosmos were the gravitational wave observatories, LIGO in the deserts of Washington and Louisiana, Virgo in the Italian countryside, and Kagra beneath Japan's mountains. Each detector is a vast interferometer, a pair of tunnels, kilometers long, in which lasers bounce with impossible steadiness. When two black holes collide, space-time ripples outward like waves from a stone cast into an infinite ocean. In 2015, humanity heard such a ripple for the first time. The faint trembling of space-time carried across 1 billion years reached Earth, recorded as a rising tone, a cosmic chirp. What had once been speculation, the collision of black holes, was confirmed as reality. These instruments now catalogue mergers, building a census of collapsed stars and supermassive beasts, tracing how often stars sink into nothing and what mass ranges their tombs contain. Each detection sharpens the boundary between theory and truth, yet black holes do not sing only in space-time's tremors. They blaze in light at the edge of destruction. X-ray observatories, Chandra orbiting silently above Earth, XMM Newton tracing cosmic bursts, and USTR hunting the highest energies, capture the violent emissions of matter spiraling into horizons. Gas ripped from companion stars or plunging clouds swirls into accretion disks, heating to tens of millions of degrees. This inferno glows in X-rays before it disappears forever. By mapping these emissions, astronomers reconstruct the physics of collapse, the spin of the black hole, the speed of inflowing matter, the jets that erupt at near-light velocities. To watch in X-rays is to watch the star's last screams before silence, on scales vaster still. Supermassive black holes are traced not only by their shadows, but by the galaxies they rule. The Event Horizon Telescope, an array of radio telescopes, spanning Earth itself, stitched its vision together to capture the first image of a black hole in 2019. The shadow of M87*, a dark circle encircled by fire, became an icon of 21st century science. Later, Sagittarius A*, the quiet giant at the heart of the Milky Way, was revealed in similar form. These images did more than confirm relativity's predictions. They offered a glimpse of the horizon itself, the very boundary where a star's fate becomes sealed. Humanity had looked at the place where something sinks into nothing, and it gazed back with fire. Future instruments promise deeper revelations. LISA, the laser interferometer space antenna, will unfurl in space like a triangle of light millions of kilometers wide. It will listen to lower frequency gravitational waves than earthbound detectors can hear, tracing the slow dance of supermassive black holes as galaxies merge. With LISA, humanity will not only detect collisions, but map the slow inspirals of titans, following them for years before they merge. Each wave will carry details of horizons, masses, and perhaps new physics hidden in the trembling of spaced ETIME.Euclid, launched by the European Space Agency and the Vera Rubin Observatory. Preparing its Orsky survey will map galaxies across billions of light-years, tracing the fingerprints of dark matter and dark energy on cosmic structure. In their maps lies the context of collapse, How stars live, die, and feed the growth of supermassive black holes at galactic cores. To understand the star that sank into nothing is to place it within the web of galaxies, to see how each collapse contributes to cosmic evolution. In laboratories, physicists are not content to wait for cosmic accidents. They build analogues of black holes within materials chilled to near absolute zero. In Bose-Einstein condensates, ripples of sound behave like light near horizons, forming sonic black holes. These systems offer a chance to study Hawking radiation, the faint glow of nothingness predicted by theory but too weak to measure from cosmic black holes. By recreating horizons in fragile matter, scientists hope to test whether information truly escapes or is lost, whether evaporation carries memory or silence. The laboratory becomes a miniature cosmos, an artificial horizon, where the fate of the star may be replayed in controlled whispers. Supercomputers extend these efforts into the realm of simulation. By solving Einstein's equations with staggering computational power, physicists watch virtual stars collapse, form horizons, and merge into greater black holes. These digital experiments reveal details too subtle for observation. The precise swirl of spacetime, the transfer of angular momentum, the birth of gravitational waves. They also allow theorists to test scenarios beyond the reach of telescopes. Exotic matter falling into horizons, magnetic fields twisting into jets, quantum effects trembling at the edge of singularities. In the simulated universe, stars sink into nothing by the thousands, teaching lessons that may one day decode real horizons. And still, instruments reach deeper. The James Webb Space Telescope peers into galactic hearts, observing the faintest quasars from the earliest epochs. These beacons, powered by supermassive black holes only a few 100 million years after the Big Bang, raise a new question. How did black holes form so quickly when the first stars had only just ignited? Did some stars sink into nothing with such violence that their remnants grew into giants almost instantly? Webb's data may answer, revealing whether stellar collapse alone explains these primordial titans, or whether unknown processes birthed them. The Event Horizon Telescope itself is being extended, its network growing with new stations and higher frequencies. Future arrays may image horizons in motion, capturing not only shadows but the dance of accretion, the flicker of jets, the pulse of plasma orbiting just outside nothingness. Such movies would transform static glimpses into dynamic revelations, showing collapse not as frozen geometry but as living process. Even particle physics is enlisted in the search. The Large Hadron Collider, smashing protons with energies approaching the dawn of the universe, has been tested for signs of miniature black holes. None have appeared, but the search continues. For such objects would confirm theories of extra dimensions where gravity grows strong at small scales. If stars can sink into nothing, perhaps matter at subatomic levels can too, leaving traces in detectors rather than in distant galaxies. Every tool is directed toward the same question: what truly happens when a star collapses? Does the horizon preserve or erase? Does the singularity mark the end of space-time or the beginning of another? No single telescope or detector suffices. Together they form an orchestra, each instrument tuned to a different register of the collapse. Gravitational waves, X-rays, radio shadows, quantum whispers in condensates. Each voice adds harmony to the symphony of nothingness. Yet even with all these tools, the mystery endures. For every detection, there is silence where questions remain. unanswered. The gravitational wave chirps confirm mergers, but do not reveal what lies inside horizons. The X-rays trace matter's fall, but never glimpse its final fate. The images of shadows show boundaries, not interiors. The laboratory analogues hint at radiation, but cannot yet resolve the paradox of information. Each tool illuminates edges, never centers. The star that sank into nothing guards its secret still. But science is relentless. Each generation builds sharper instruments, listens with finer sensitivity, dreams of greater precision. To test horizons is to test the very foundation of physics. It is not only the fate of stars at stake, but the fate of theories, of relativity and quantum mechanics, of the unity of natural law. The black hole is both grave and crucible, where tools are forged not only to study collapse, but to redefine. Understanding in this pursuit, humanity confronts its own scale. The instruments that capture whispers of collapsing stars are vast kilometers of laser tunnels, satellites spanning continents, computers consuming entire facilities. They are monuments, built to listen to the silence left by a single star's fall. And yet, for all their immensity, they remain fragile ears pressed to a cosmos that speaks in riddles. The star may have sunk into nothing, but through telescopes, detectors, and simulations, its silence becomes the most profound conversation ever recorded. Science listens, interprets, refines. Each result does not close the question, but sharpens it, revealing how much more lies hidden. The horizon has not yet surrendered its secret, but every tool extends the reach of human vision a little further into the abyss. The star that sank into nothing did not end with its collapse. Its silence remains, woven into the fabric of the universe, echoing through the minds that dare to contemplate it. For though the star itself has vanished, its disappearance leaves a question burning brighter than any nuclear furnace. What does it mean for something to fall into nothing? For millennia, stars were symbols of permanence. They guided travelers across oceans, inspired myths, and stood as emblems of eternity. To human eyes, they seemed changeless. But the collapse of a star into a black hole reveals another truth. Even the greatest lights end. Permanence is an illusion. Eternity, at least in the form of shining stars, is fragile. And yet, paradox remains. For in dying, the star may not have ended. It has transformed into something unseeable, something that devours not only matter and light, but certainty. Its horizon is a veil across which human knowledge falters. Beyond it lies a realm where the rules of physics may fracture, where geometry and causality dissolve. The star is gone, but in its absence it has opened a deeper space, a space for wonder, terror, and reflection. If a star can collapse into nothingness, what of all else? What of planets, galaxies, perhaps even the universe itself? Black holes remind humanity of its scale, fragile, fleeting, vulnerable to forces that dwarf imagination. But they also remind humanity of its capacity to even ask such questions, to measure the silence, to imagine what lies beyond. In contemplating the collapse of stars, humankind confronts both its smallness and its greatness. Philosophers once asked whether nothingness could exist. Is it an emptiness or a fullness beyond? Perception. Black holes transform that ancient riddle into physical form. They are places where something becomes hidden so completely that it mimics nothing. The star that sank into nothing has not ceased to be. It has been folded into a secret. To call it nothing is to acknowledge the limits of sight, not the limits of reality, the lesson is profound. Nothingness is not void, but boundary. It is the edge of knowledge, the place where theories falter. For some, this boundary is frightening, a cosmic erasure, a proof that meaning can vanish. For others, it is liberating, a promise that there is always more beyond, more to question, more to seek. The black hole becomes both grave and door, ending one chapter of reality while suggesting another hidden behind it. In this sense, the star's collapse is not tragedy but transformation. Its mass, its light, its history are not gone. They are compressed, encoded, transfigured. Perhaps they are preserved in holographic memory on the event horizon. Perhaps they seed another universe, inaccessible but real. Perhaps they dissolve into quantum foam, their essence scattered across space-time's deepest fabric. Whatever the fate, erasure is never simple. The cosmos seems to guard information, to resist true oblivion. The star's memory may remain, though hidden in forms unrecognizable, and still the philosophical weight grows heavier. If the star's light is gone, how do we speak of it? How does something exist if it cannot be seen, touched, or measured? Do black holes exist in the way mountains do, or in the way ideas do? Inferred, indirect, real, but never present. The collapse of a star raises not only physical paradoxes, but ontological ones. It asks what it means to be when being itself can be swallowed. On the human scale, this reflection becomes intimate. For what are human lives but brief stars, burning with fleeting brilliance before fading into silence? The collapse of a star mirrors the arc of every existence: birth, fire, exhaustion, and disappearance. To contemplate the black hole is to confront mortality itself, not as metaphor but as cosmic structure. If even suns sink into nothing, then so too will everything smaller. But perhaps, like the stars, disappearance is not pure absence, but transformation. Memory, impact, echoes, these may remain encoded in the universe, however faint. There is a humility in this vision. Black holes remind humanity that knowledge has boundaries, that science cannot yet penetrate every horizon. And yet, in recognizing the boundary, humanity gains wisdom. The acknowledgement of ignorance becomes a form of understanding. To admit that a star has sunk into a place where no light returns is to confront mystery not with defeat, but with reverence. And what of the future? The universe itself may one day face a collapse or a fading. In a far-off epoch, stars will exhaust their fuel, galaxies will dim, and black holes themselves may evaporate through Hawking radiation. If so, even the star that sank into nothing will, at last, release its essence back into spacetime. The nothingness itself will fade into nothing. What then remains? A silence deeper than silence, a cosmos emptied of memory. Or perhaps a new birth, a rebirth into structures that human imagination cannot yet shape. The story of the star that sank into nothing is, in truth, the story of boundaries. The boundary between fire and collapse, between light and darkness, between knowledge and mystery. It is a reminder that every end hides a beginning, though not always one that can be seen. It is a reminder that science and philosophy are twins, born of the same longing, to ask what lies beyond the visible. And so the closing image lingers, a cathedral of vanished stars, their light extinguished, their bodies hidden behind horizons. The night sky sparkles with the brilliance of countless suns, but woven among them are graves unseen. In every galaxy, in every epoch, stars have already sunk into nothing, leaving holes that shape the cosmos itself. They are silent, but their silence speaks. The silence tells of gravity's power, of spacetime's fragility, of the unity of nature's laws. The silence tells of questions unanswered, of mysteries that may never yield. But above all, the silence tells of continuity, that nothing is ever truly lost. Only transfigured, that the star that sank into nothing is still here, though unseen. Its gravity sculpts galaxies. Its shadow shapes the light of distant matter. Its paradox challenges the theories of greatest minds. Its silence inspires generations to build instruments, to imagine equations, to stare into the abyss. And for humanity, that may be the greatest legacy. To know that even in disappearance there is meaning. To know that even in nothing there is something. The collapse of a star becomes not the end of knowledge, but the beginning of wisdom. As the narration fades, imagine once more the star, brilliant, immense, forging the atoms of life. Imagine its collapse, its sinking into a silence so absolute that no light returns. Imagine the void it leaves behind, blacker than any night. And then imagine this truth, that in its silence the star still speaks, whispering of the deepest riddles of time, space, and reality. The star has not simply vanished. It has become a mystery, eternal and unyielding, a star that sank into nothing, and in doing so illuminated everything.